fundamental concepts in fluid dynamics. If you see, it is almost as equivalent as studying electric field when you are studying electrostatics. So it's almost same like studying velocity fields in fluid dynamics. So velocity field is nothing. It is almost analogous to electric field when you're studying electrostatics, but it's nothing but it's here we have velocity, there we have electric fields, but here it's a slight difference there. Slight difference you can observe. To understand velocity field in the most easiest way, consider there's a lake with a flow of water. We consider the water flow is actually going straight and does not have any deviations, but this is very ideal condition. But in reality, if you see, the actual straight line rectilinear motion is actually not true. If you go into deep, every point in the water flow has a different direction of velocity with different magnitude. It depends on the space, time, and coordinates of the particular point. Here you can just see 2D plane here, x comma y. It's just a lake water flow of water in a lake. If you observe here, this is how the real situation actually looks like. The velocity vectors at each and every point in the space. Example, consider a plane, xy plane, and you have different velocity vectors at different points. Like this example, yeah. Let's take a pen. Different velocity vectors in different points. Here, what's changing is x comma y. Here, this is one point, this is one point, this is a different 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 point, and the velocity has different directions in the different space and different times also. So this velocity vector field is constrained to space. Space we represent using x, y, z, and time also. It depends on the time, it depends on the space. Today we'll just discuss how to determine streamline flow. And one more important thing is you can observe velocity field in weather maps. If you see the open access weather maps of satellites, you'll see the small arrow type things going like a tornado, going like a hurricane. It's nothing but a velocity field of that particular water body and the fluid flow. So next time when you're seeing weather map, think it as a velocity field. Then you'll get a good picture of understanding of velocity field. That's all about a velocity field. It depends on space and time. It's nothing but velocity. If you had to simply define it, it's nothing but velocity assigned at each space point and time point. That's all about velocity field. Today we'll do how to get this stream. This is called flow. This is called a streamline flow. How to get this pattern or a streamline flow when velocity fields are given. So velocity fields are known here. The unknown thing is how to actually draw the streamline flow when velocity fields are given. That is our job to do here. We just do it quickly, learn it, and this is very fundamental and very important also, very important concept. For example, today we are just taking two velocity fields, x square minus y square. You can see it depends on x comma y, so it's 2D here. Let's restrict to 2D because 3D makes the scenario more complex actually. So let's restrict ourselves to 2D. We have two velocity fields, v is x square minus y square, and u as we'll just take v as minus 2xy and u as x square minus y square. These are two velocity fields in 2D. Now our job is to draw streamline flow. That is how the flow actually behaves when the velocity field vectors are given. That is our job. To do that, our approach is to go through differential equations and derive the potential vector. If you know the numerical methods in mathematics, then that would be an advantage to solve these problems. If you don't know, just follow the process which I came up with. This is the easiest process we can come through, or else the bigger explanation will be a mathematical one, which is of course numerical methods, and to explain all the numerical methods it takes a lot of time, so we'll just skip that part. But the main thing we are using here, the method is numerical methods of mathematics and differential equations, basic differential equations, to solve this and get the streamline that we wanted. To start with, we all know that dy by dx is nothing but slope. It can be defined with v by u, we know that. So that becomes minus 2xy by x square minus y square. So if you just cross multiply things, it is x square minus y square into dy, there is dy part, and 2xy into dx is equals to 0. Let's rearrange it quickly. that becomes 2xy dx plus x square minus y square. And now if you are someone who is very similar with numerical methods and differential equations, you'll get a very general form of differential equations, that is m dx plus n dy. So in the place of m we have 2xy, in the place of n we have x square minus y square. So what we do is, before proceeding to find our streamline function, which can be used to plot a streamline flow, that is how the flow is behaving. Before doing that, we have to check whether the given differential function is exact or not. And to know why to check whether the differential function is exact or not, that's the concept of maths. We'll discuss it later, and it's a bit complex and takes a lot of time. So for now, to check whether a differential equation is exact or not, if the differential equation is in this form, what we just do is we take the partial differentials of m comma n with respect m we take with respect to y, and n we take with respect to x, and they has to be equal. If they are not equal, we say the differential equations are not exact. If they are equal, we say them as exact. That's the basic principle we just follow here. So if we just do it quickly here, we get dm by del, this is partial differentiation, you know that. So we keep x as constant here, so we get del m by del y as del by del y of 2xy, and x is y is we are doing with respect to y here, so x is constant, we get 2x. And now we'll do with respect to x and n here. If we take this combination, it's x square minus y square, we are doing with respect to x, and y is constant here. Since it is a partial differentiation, we get 2x. So that means our partial differentials are equal. So now we can say the given differential equation is exact, and now we can proceed further for finding our streamline. If it is not exact, the story becomes different. Since it is not it is exact, we'll just proceed to find our streamline, and I'll explain what happens if it is not exact, or what's the mathematics behind it. If you want it, please comment down. I'll explain that part also. Since we are just focusing on the physics part of it, I'm not going into too much mathematical part of it. If you really want mathematical part of it, please comment down. Okay, since now the given differential equation is exact, I'll just quickly rewrite the differential equation. It's 2xy dx plus x square minus y square and dy is equal to 0. So this is our main job to do when they have given two different functions of velocity field. The first thing we have to do is we have to form a differential equation in terms of dx and dy. Then what we do is we have to find our potential our required one, which is streamline flow, how it is actually behaving with respect to x comma y. After this, we can just proceed quickly. Let us assume, since this is a 2D, let us assume our streamline flow is in two dimensional, and it is in xy direction. So we'll assume the streamline flow as phi of x comma y, and our job is to find this. Now, since we have this differential equation, this has to come from this. One of the solution of this differential equation has to be the streamline flow. So we'll assume that solution as phi, and now we'll just do the reverse engineering. That is, this is m here. We'll just integrate this part with respect to x. So m dx should be equal to phi, because one of the solution of this differential equation is nothing but our required answer. So we'll just consider f of x comma y is integration of m with respect to x. That is 2xy dx, which gives us 2x square by 2y plus since we don't know, since it's a multivariable calculus here. We have two variables here, x comma y. We'll get a constant function in terms of y, because we are just integrating with respect to x, and we are not sure whether this function has y or not. So we just consider it as f of y as a constant function. So we'll get our function as f of x comma y as x square y plus f of y. So that's it. Now our job is to find f of y. Then we'll be having our streamline function. You can just plot it in our plot it in our graph, and we'll get the flow, how the flow or fluid is actually behaving with this particular velocity in this particular velocity field. So this is n, and we'll differentiate this with respect to y, the phi we got. So that is del phi by del y. We'll have x square, if you see, x square with respect to y, x square, and into 1 plus f dash of y. And del phi by del y, if you see, is nothing but it's one of the solution, that is n. And here del phi by del y, we can just write it as n, because this is a part of dy portion here, x square plus f dash of y, and we just replace n with x square minus y square is equals to x square plus f dash of y. X square get cancelled, and minus y square is equals to f dash of y. If you just integrate with respect to y, dy on the both sides. this is differential and integration. It gets we'll get f of y as minus y cube by 3. So we just obtained f of y in this way. If you see this method in mathematics, in numerical method, this is called something called scalar potential. This phi function, we just obtain the scalar potential from the differential equation. That's it, nothing else in here. After obtaining f of y, we can just replace that. F of x comma y just becomes x square y minus y cube by 3. That's it. That's it. We got the streamline flow of the any fluid which has these particular velocity fields. That is important. So whenever you get velocity fields like this, they ask you to find how the fluid actually behaves. So this is the procedure we have to follow here. We have to obtain the streamline flow here, and to plot this, let's consider this as c and x square y minus y cube by 3. And we'll take for different values of c, we'll get different values, and if you plot them all, we'll take one case, that is 0 is take y as common here, x square minus y square by 3. So one of the solution is if you see here 0, equate this to 0 plus or minus root 3 by x. So that's like straight line, two straight lines passing through alpha. This is one of the solution of this flow. If you put all the values, example c equal to 1, 2, 3 and many other values, try this exercise here. It will be a fun. If you try to draw for all the c values, you'll get something like this. You'll get a graph something like this. This is how fluid actually behaves when we have velocity fields as v. If you remember, it's minus 2xy. Here we have started the problem here. We got two velocity fields, and our job is to find how the fluid behaves. So if you see, these are minus, if you see here, these are root 3x minus root 3x. These are one of the solution when c is 0. When the c value differs, the values, the streamline flow actually differs. This is how the pattern you get, a beautiful pattern in this vector field. And the vector field, if you draw, vector field is nothing but vector directions accordingly in the fluid flow, in the streamline flow. And this is two-dimensional. This gets more interesting when it goes to three-dimensional. But for now, we just discuss the two-dimensional, and this is how you'll obtain the you'll obtain the streamline flow of any fluid when vector fields are given. Okay, this is specifically when the vector fields are given. If the vector fields are not given, there is a different process. But if the vector fields are mentioned, and your job is to find the streamline flow, this is how you proceed. You just for just a quick revision, you just take the slope of it, form a differential equation, check whether it is exact or not. That's an important step, and then assume a solution of this equation, that is as phi or any function, and then integrate it, do reverse engineering and do some maths, and you'll get the streamline flow. And this is very important. This is I think the fundamental of fluid mechanics. If you want to proceed further, this is the basis of velocity field. How does velocity field works? Because as you progress in fluid dynamics, you get lot of other things, lot of very important things: irrotational, compressible, incompressible, many other very crucial and important things. But the basis, if you see the basic or the origin, if you see, it all starts with velocity field. So learning about velocity field and having a good clarity and conceptual clarity of it is very important. And this is how our velocity field looks for this particular functions. I hope you understood how to derive the streamline pattern from the velocity fields given, and you appreciate the beauty. I think you also appreciate the beauty of fluid mechanics, aerodynamics, how complex it is, and how perfect is it, and how nature perfected it in the reality we see around. I hope this video is useful for you. If you really felt useful, please subscribe for more videos like this, and we'll see you in the next video. Thank you.